Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're looking at a problem with refrigerant R134a. Let's talk about what that is. And we're solving for thermodynamic properties. So again, basic problem, introductory problem for properties of pure substances and how to find and identify the state of these substances. The problem statement reads, 10 kilograms of R134a fill a 1.348 meters cubed rigid container at an initial temperature of minus 40 degrees Celsius. The container is then heated until the pressure is 200 kilopascals. Determine the final temperature and the initial pressure. Okay, so first things first, what is this? Well, this is a refrigerant, right? That's what R stands for. And this is a fluid that is used commonly in refrigerators and air conditioners. So if you have a fridge at home, the gas that goes inside, on the back coil, expelling heat into the environment and goes inside, taking heat away from the inside part of the fridge, that fluid is probably, most likely, R134a. It was introduced to substitute the famous CFCs, the chlorofluorocarbons, because of the Montreal Protocol. Because, as you guys probably know, this was very bad for the ozone layer, right? So it was very destructive for the ozone layer. And then what this refrigerant is like just the fluorocarbon, right? So it's a molecule that has 2 carbons and then 4 guys like so, and then hydrogen, and no chlorine. And then this does not have an impact on the ozone layer. It does not interact with ozone and destroy the ozone in the ozone layer. However, it's a very potent greenhouse gas, and therefore it's also being phased out, and we should start to see other refrigerants take place in the next couple of years. So what do we need to do here? We have 2 situations, right? We have a container and a rigid container, mind you. The rigid is that special word that we already learned. That means that regardless of what happens with the fluid inside, the volume of this container will not change, right? So therefore the volume throughout this heating process will be constant, right? So that rigid there always gives you that hint. And we're going to have 2 states, right? In both states we have the same R134a. And in the first state we have 10 kilograms. We have a volume of 1.348 meters cubed. And we also know that the temperature here is minus 40 degrees Celsius. And on this side, so we're adding heat, right? So we're putting some heat in. And then on the other side here, we have exactly the same thing. So the volume, mass, and the substance itself did not change, right? So we didn't have any mass going, entering or leaving the system. We only had heat entering. And we expect our temperature to increase, right? Because we're giving heat to the system. And we're given that our pressure here is 200 kilopascals. There you go. Okay, so whenever we have thermodynamic properties, to identify or to find all the properties of a state, we just need 2 properties to start with. Okay, and in this case, it's very obvious that the temperature is one property that we have on the first state, and the second property we have is the specific volume, right, which is the ratio between the volume and the mass. And on this case here, on the right-hand side of state 2, same thing. I had different properties, yet I still have 2, right? It's the pressure and specific volume that did not change whatsoever because the container is rigid. So what I need to do here is I just need these 2 properties. So let's write down here state 1. State 1, temperature is minus 40 Celsius, and my specific volume on state 1 is equal to the volume divided by my mass. In this case here, 1.348 divided by 10, so easy, 48 meters cubed per kilogram. So these are 2 properties, and with these 2 properties, that allows me to calculate, or to find, I should say, all the thermodynamic properties of this given state. Okay, how to do that? Well, I go to my property tables, okay, and I have all the properties tables here. I'm going to leave the PDF of this for you in the link in the description. All right, so I'm looking for minus 40, and that's quite easy because I'm looking at the temperature table. So I'll go minus 40 degrees here, and I'm going to look. This is a saturated property table, so let's try to identify if we have a saturated mixture or not. Our specific volume is 0.13, okay? If this were a saturated liquid, our specific volume would be 0.0007. If it were a saturated vapor, our specific volume would be 0.36, Okay, note how our value is between these two, right? So our value, our 0.13, is between the 0.007 and the 0.36. So therefore, because of that, I can be sure. So I'm sure this is a saturated mixture, right? What were the options, right? If it weren't a saturated mixture, what could it be? Well, we talked about this before, but if we draw quickly here a TV diagram and we draw the dome, and we got the dome here, boom. Anything inside the dome is going to be saturated mixture. Anything to the left of my dome is going to be a compressed fluid or a subcooled fluid. Anything to the right of my dome is going to be a superheated fluid, right? So right here on the edge, the specific volume, if I were to read the specific volume here, this guy would be 0.3, what was it? 36 something, right? 36 something. If I were to read the specific volume over here on the left-hand side, this would be 0.0007 something, right? And because my value is 0.13, I know it's going to fall here in the middle. If my value, right, if my specific volume were greater than 36, it would be on this side here, and therefore I would be looking at a superheated fluid, which means that I'll have to go to a different table, right? If it were on the left-hand side, that is, if it were smaller than 0.007, I would have to go to a compressed fluid table, or depending on the pressure, I could use the properties of the saturated fluid. We're going to talk more about that as that case comes along in other problems. But for now, I'm sure this is a saturated mixture, and therefore, if that's the case, all these properties are valid. Okay, so that means the pressure has to be 51.27. There's no other option. It means that my internal energy is going to be somewhere between minus 0.036 and 207.38. My enthalpy is going to be between 0 and 22586, and my entropy is going to be between 0 and 0.96869, right? So all those properties I know of because I've defined the first state. So the question is asking us what is the pressure, right? So the pressure, so therefore pressure on state 1 is equal to 51.25 kilopascals, and that is our answer for part A. Okay, and then B, or not B, it's just one thing, but the second part is asking what is the final temperature? So that is in regards to this state here, state number 2. And again, for state number 2, we know two things, right? We know that state number 2 has, let's write it down here. We know that state 2, we know the temperature, we know the pressure of state 2 is 200 kilopascals. And we also know that the specific volume has to be exactly the same as the specific volume of state 1, right? So therefore, the 0.13 we found before, 0.1348 meters cubed per kilogram. All right, so now I have a pressure, not a temperature, so I cannot use this table. I'm going to have to scroll down all the way into my pressure table, and here's my pressure table. So I'm looking at pressure now, not temperature. And I'm looking for 200 kilopascals here, so I'm looking for this guy here. Right, and again, my specific volume did not change, so I still know it's the 0.13, right, the 0.13. So therefore, same thing I'm going to do here. So 0007 and 0.09. So guess what? Now my specific volume is greater than the specific volume of the saturated vapor. So that means, that indicates that my mixture is a superheated fluid, right? Not a saturated mixture anymore. So as I'm giving heat, so let's put it like this, because the specific volume of state 2 is greater than the specific volume of the saturated vapor, because it's greater, I know state 2 is superheated. Okay, so if I know that, then I know that the temperature is not minus 10.09, and to be able to find the temperature, what I need to do is go to the superheated table. So this table is not the one that I need to get my properties, because this is for the saturated refrigerant, and this is not saturated, this is superheated. So I'm going to keep scrolling down all the way to my superheated table here, and now I'm going to go again and look for 200 kilopascals. Note that we have 0.6, 0.1, and 200 kilopascals is the same thing as 0.2 megapascals, right? Same thing. So I'm interested in this square here. This is where I'm going to find my properties. And I'm looking at the specific volume, and I'm interested in the 0.13, right? 0.13 is the one that we found for our state 2. And I'm going to know that 0.13 is going to fall here, right? Specifically, we had 0.1348, correct? So it's going to fall between these two values. So therefore, let me Note that I'm going to be reading out the temperature here on this left-hand side. So let's just highlight these guys. Okay, so therefore I know that my temperature of this refrigerant on state 2 is between 60 and 70 degrees Celsius. To be able to find out which temperature exactly my final temperature is, I need to interpolate between these two guys. If you don't know what interpolation is, I'm going to leave you guys a link here on the right hand side for you to check it out. And if you want to know how to do interpolation, again, I'm going to leave another link of another video that teaches you how to do in different ways so that you can find the one that suits you best. All right, but the way that I always organize this is like so. I'm going to do my 60 Celsius here. I'm going to do my 70 Celsius here. I'm going to do my specific volume. So my 60 is 0.13206. And for my 70, that's 0.13641. And I'm interested in this temperature here that I'm not sure. And this is the temperature for 0.1348, which is the one that we know to be our specific volume, right? So I'm going to be interpolating between these two guys here to be able to find my temperature. And when I do that, and again, you can do that using the links provided before to know how to do it, you get that the temperature for your state 2 is 66.3 degrees Celsius. And that will be our answer for the final temperature of this problem. Okay, note that whenever you're doing interpolation, the idea is that because this value here is in between these two guys here, then your temperature has to be in between these two values here, right? So if you were to find anything that was not between 60 and 70, we did something wrong. We need to go back and do it again, right? So 66.3 is consistent. 13.48 is closer to 13.641 than it is to 13.206. So therefore, it should be closer to 70, and indeed it is. So all good there. All right. So I hope this helped you out. If you have any questions, leave them down below in the comment section, and I'll be sure to address them. If you like this video, please leave a like to the channel, and we'll talk soon.